All right, welcome back to Advent of Code. If you've made it this far, congratulations. We're more than halfway now. Let's see what we've got going on for day 14. Bathroom security has been, quote, improved. Okay, we got a list of robot positions and velocities, one robot per line. Robot positions, X represents the number of tiles the robot is from the left wall, and Y represents the number of tiles from the top wall. So we've got a left to right, top to bottom coordinate system. So position of p equals 0, 0 means the robot is in the top left corner. Velocity is vxy, tiles per second. I have a feeling this one's going to be fun to visualize too, with all the little robots moving around. So velocity of v negative 2 means that each second the robot moves one tile to the right and 2 tiles up. Robots outside the actual bathroom are in a space which is 101 tiles wide and 103 tall. However, in the example, the robots are in a space which is 11 and 7 tall. So our test case is different from our actual input. So the robots are good at navigating over under each other, so they can share a same tile, which is wonderful. Don't have to worry about robot collisions. Okay, they can teleport. When they run into the edge of the space they're in, they instead teleport to the other side, wrapping around on the edges. Simulate for 100 seconds. So I assume this is going to be part 1, actually simulate, part 2, another example like yesterday where we can't actually simulate it in the amount of time that we have. So to determine the safest area, count the number of robots in each quadrant. Robots exactly in the middle don't count as being in any quadrant. So we basically get to take out the middle horizontal axis and vertical axis completely. Count the robots, and then there's a safety factor of 12. Predict the motion of the robots in your list within a space that is 101 by 103. What will the safety factor be after exactly 100 seconds have elapsed? So these are looping, is something that is worth calling out. Whatever positions they make it to are going to be the same positions they're in every time they loop over. Do we have diagonals? I think we do have diagonals. Yeah, -2, -2. So we have to deal with edge wrapping here. So I wonder if the answer is going to be calculate the loop for each robot and then basically take the like 112th item, etc., like that kind of thing. Because we could do the loop for each robot, and then once it overlaps with a previous position, then that finalizes the loop. We can have that for everything. Our puzzle input is, I don't know, some amount. So let's get started here. Just create day 14, grab the test input, this. I want a robot struct, I think, where a position is an IVEC2 and a velocity is an IVEC2. Oh, derive robot, derive debug. Brain somewhere else right now. Cargo toml, we need to pull in glam. Again, these could be tuples for you. I use IVEX because it helps me keep in mind where my X's and Y's are. So I can do .x and .y instead of .0, .1 kind of things. So we'll end up with basically a robot that has a position and a velocity. The position will be something we can keep updating. Although I think in the end, we probably don't need to just simulate it. We need to do something more. Maybe we'll simulate it for part 1 and then do a more advanced solution for part 2. I do think that looping is going to be relevant once the grid gets larger. So if we have a parse function, we can write this kind of in line here, separated by line ending, and then we basically have a robot parser. So we'll preceded p equals separated pair. What are we going to use? I32s, complete I32, tag comma, complete I32. And I don't think I've ever said it in any of the other videos, but I do complete I32 instead of I32 so that I don't have any confusion about which I32 I'm using. Because right now that's not imported, right? Or not brought into scope. So it looks a little bit weird to have I32 here like that. And that's really the only reason that I write complete here. I just find it more readable. All right, so we've got separated list, line ending, preceded. That's our first. And then we've got another separated pair. Or we could do, right, so separated pair, preceded that. Then we'll call it space 1 with another preceded tag v equals, and then exactly the same thing here. So this is one of the interesting things about kind of nom and the way we're using it here. Can we write this all in line like this? Absolutely. Do you see that there is repetition here that we could break out? Also, absolutely. So this could get broken out into an IVEC2, right? And I'm going to call this parse IVEC2. So we could write this like this then, right? That's exactly what we just pulled out. And we're turning it into an IVEC2 here. So we could have IVEC2 here, and that's really the same thing as having separated pair.map here. So now we end up with these significantly less code here, and we parse an IVEC2 here and there, and we get different precededs for those IVEC2 separated by spaces, and a bunch of them line endings. And we can map over this, and we've done this before, so we're just running our parser. If there's an error because that returns a result, then we're mapping that into something that we can return with a little bit more context, and we'll just debug out robots. So our first robot is 0, 4, 3, -3, and our last robot should be 9, 5, -3, -3, and it is. So we have everything ready to go. So thing we can do for part 1 anyway, we do have to do the thing we did yesterday for the test values. So let's see if I can. So here's our tile sizes, and it's 100 seconds on both of them, right? Where will they be after 100 seconds? So this will work for us. We either have, if we're in a test, a map size of 11.7, and if we're not, 101, 103. I think I read that correctly. Yeah, 11.7 and 101, 103. And it's 11 tiles wide. So what that means is the length is 11, which means 0.11 exclusive is the size of the board. So for mute robot in robots.ittermute gives us a mutable reference or an exclusive reference to each robot in this vec. And that means the position is plus equal the velocity. And this won't work for the wrapping, right? Just to be clear. But one thing we should be able to do here is impl display, which is standard format display. We'll implement missing members, which gives us this function here written for us. And this theoretically could work, actually, but now that I'm thinking about it, we can have multiple robots on one spot. So I think I want to represent it with numbers. But we can use the right macro to take this formatter and format this value into it. In this case, we don't really have a lot to, I guess, format for just a single robot, but we can absolutely do this. And if we want to debug the grid, we can take in the robots, which in our case will be a slice, and we'll use the const here, right? So for y in 0.map size y, and for x in 0.map size x, and robots.find or .iter.find, because we have a slice here. And if we find one here, we can match, fill the match arms. If some, we'll have a robot here. So we can print robot. And if none, we can print, I guess, dots were the empty spots. And in between all of these, we probably want to print line before we do everything. And then after each loop is the way that I'll do it. So if we take this debug grid, we put it here and pass in robots. Hopefully we will see all of the locations of all the robots, which looks like 1, 1, 2, 1, 1, 1, 1. So we really should be doing probably numbers here. That's how they're doing it. So I think we change this to a filter, which would be really easy for us to do, right? Match. And then if we match on length, then none is 0. And otherwise, we're just going to print n. Actually, this is not length, this is count. So if now we look at it, then we get 1, 1, 2, 1, 1, 1, 1, 1, 1, 1, 1, which looks right to me. So now we have debug grid here, and we can dump this after this, and we see the next one. So this is step 0, this is step 1. I think step 1 is going to be wrong because they aren't looping. So we need to loop here, right? How do we loop? Well, we could do robot.position plus this mod map size, I think will work. I actually can't say that I do this operation on IVEC2s very often. So this will be a check for both of us to see if this actually does what we need it to. Oh, this is just the one robot. And this is after 100 seconds. Okay, cool. So it doesn't give us step 2 at all. That's unfortunate. That's really annoying, actually. 2, 4, 2, -3. So that's this one. That's really hard to follow. Unfortunate. We could change our output to just show this one, but I'm pretty sure that our math will be correct. So we can just wrap another loop around this. And actually, we don't need the mutable there because we're iter muting. So this is a mutable reference and we're not modifying the value of the robot variable. We're modifying through that exclusive reference there. So theoretically, this will run. So I'm very confused about the output that we're getting here. We only see 2 robots at the very end. And now that I think about it, I feel like we don't need rem or mod rather. I feel like we need rem Euclid because of its behavior on negatives. So let's see what this looks like. 2, 1, 1, 1, 1, 2, 1, 1, 1, 1, 1, 12, 1, 1. Okay, so yeah, we needed rem Euclid and not mod, which is something that has come up in past adventive codes. So semi-expected. So this is for vec2s. I don't want vec2s. Scroll. IVec2. It's going to be the same thing, but so if we're on the IVec2 docs page, right, and we look at the left sidebar here, we see a bunch of trait implementations like add assign, bit or div, etc., etc. One of these is going to be rem, and rem is responsible for applying the percent operator. And we can go to the actual docs and say, this is the remainder operator. Read as much as you want to about that. But rem Euclid is not part of a trait. And this specifically does the Euclidean division, which if we go into the standard library, calculates the least non-negative remainder of self-mod right-hand side. So roughly speaking, that's why we're using it. So now the next thing we need to do is to actually separate this into quadrants. So my question here, I'm going to get rid of this print line here. Probably going to also get rid of these debugs. And then we have, what is this? 11 and 7. These are always going to be odd sizes. So if we do map size over 2, we'll end up with 5 and 3. And then quads are 0, 0.halves.x and 0.halves.y. So that's quadrant 1. And halves.x equal map size x, also with 0 halves y. And then halves x and halves, I should have named that something else. Halves is such a weird word. Halves y map size y. And that should be the 4 quadrants. I guess this should be quadrants. And then we get quadrants.iter.map quad, where quad is a range, or 2 ranges actually. And then the answer for this is going to be robots.iter.filter robot. I guess we only care about the position, right? Robot position ... And then this is xy. So x dot contains, I guess let's name this x's and y's. And this is a tuple. So x's dot contains position.x and y's dot contains position.y. And we need to count this. And I think we need to sum this. Are we summing? Multiplying. We're multiplying. We need to sum this into something that is reasonable. I don't know what that value is going to be like. Oh, we changed to usize because we counted. So we'll do usize here. So this count returns a usize. This map returns a usize. So when we product, it's got to be usize. And then, okay, result dot, well, that's not right. Okay, result dot toString. And with any luck, that'll pass. Did we not put the number into the test? I forgot to put the number into the test. What is the... Okay, safety factor of 12. So we got the wrong answer. We have 12 on the left, 36 on the right. Let's inspect some of these counts. So here we'll get x's and y's and count. So we've got 0 to 5, 0 to 3 is 1, 3, 6, 2. 3 to 7. 1, 3, 6, 2. 1, 3, 4, 1. Oh, because we're not supposed to include the 5. That's why. It is this plus 1 in both cases. So if this is on the lower side of any range, we need to skip that one because it's inclusive of the bottom and not on the right. This is our display from earlier. Our display implementation fizzled out. We don't really have a reason to have this, so I'm just going to delete it. Our test looks like it's passing. Let's run it again just to make sure. We can force it to fail, and then it passes. So cool, good. Not planning on needing to debug that count anymore, so I'm going to get rid of this extra code. We get a Clippy warning here for debug grid. Function debug grid is never used. This is a dead code warning. So I'm going to use this little attribute macro here to allow the dead code warning, but just for this item, because I want to keep the debug grid around, but I don't necessarily always want to use it. So now we can run, what are we on, 14? Starting to forget what day we're on. Day 14, part 1. And this runs really quickly. I assume that this hopefully is the right answer. But also I assume that, what is the fewest number of seconds that must elapse for the robots to display the Easter egg? A picture of a Christmas tree? what is a Christmas tree supposed to look like? What is that? What is a Christmas tree? Okay, so I'm going to be real honest here and go, I don't even know what this would qualify as. I have no idea what to look for. Like, how did this person decide to draw a Christmas tree in the output? I don't know at all. How do I find out? I guess running it and figuring it out. There are no hints here at all, as far as I can tell. And that's all really frustrating. Luckily, the Discord, who is also going along with Advent of Code, has communicated what the condition is for this to happen, and it's if none of the robots are overlapping. So maybe we'll print out the Christmas tree and take a look at what it should look like together. So we'll take all our code for part 1, we'll dump it into part 2. The test isn't going to matter at all, right? We have no way to test this because we don't even know what we're looking for. This is going to be basically infinite. So the thing that we're going to be looking for, because somebody in Discord has communicated that this is actually the condition that we need to check for, is making sure that all of the robots are not overlapping. So I'm going to replace this with a loop, if I can type the word loop. We're going to set I equal to 0 outside of the loop. And then the question is, where do we do the check? I think we do this afterwards. So I plus equals 1 here. We're still looping all of the robots. I still believe that there would be a theoretical loop here. That would be what we need to do if we wanted to speed this up. So we have 2 options here. We can either use loop and put our condition, I guess, down here, or put our condition here and put a while loop, but we still need our condition no matter what. So I'm going to call this a tree test. And I think we just need all the robots to do that. So if tree test break with I, that means that this will be our last step. Tree test doesn't exist, so we need to make it. I'll use Rust Analyzer to generate a tree test function, which generates tree test down here for us. Robots is going to be a slice of robots, I guess. And this will be a Boolean. So the question is, are any 2 robots on the same? I guess we could build up some kind of hash set or like build up a map or something like that. I don't really like any of those options, but I don't know that I like doing combinations either. Because if we do combinations, then we have to check every pair, which will be 500 combinations of 2. Seems like a lot. Whereas I think we can just do like 500 insertions. So let map equals, I don't know, hash map. And this will be nothing. We're just going to be constructing a hash map every single time. I can probably think of something that would be faster than this. We could also use a different hasher for the hash map. This will be what? IVEC2 as a reference, and we'll call it a U8. Just make it small. I guess we could also call this a Boolean because it doesn't matter. I think this could also be unit. So actually we don't need it now that I think about it because we only need the hash set. I don't actually know that building the hash set is going to be faster than iterating through. This is not robots. This is robot. Dr. Robotnik. Right. So robot and robots. Robot has a position. Again, we don't care about the velocity at all. We have like an insert if, because we can definitely do contains position. If it contains the position, then we return false out of everything. And if it's false, if it doesn't exist, then map.insert position. And if we get through this whole thing, then we are true, right? And we can't construct a hash map when we have a hash set. So theoretically, this should work. And then this doesn't matter at all. And we get last step here. And I just kind of really hope this works. We get a number. Do we think it's the right number? Do we just try it? I think we just try it. That's the right answer. Huzzah. So, because this is so disastrous in terms of a question, we are also going to debug the grid. But I think I want to write this out to a file rather than printing it. So I think I'm going to take these print lines and we're going to let mute output equals string here. We could do string with capacity here, but honestly, I'm not concerned about the allocation at all. We want to pull in standard format right here. And then we also want to do that for our prints. We're going to change these to write and do nmute output. And then probably both of these need to be wrapped like that. Now, all of these, it should warn us. Let's do cargo clippy day 14. It should warn us here that these are results that are not being used. So unused standard result, that must be used. That's because write returns a result. In our case, this should never fail. So I'm just going to unwrap it and that would work. But instead we can do a question mark here and we don't have a return value. So let's make the return value result. Let's say we're going to return a string and I'll call this unit for a second just to see what the type error is. And the first thing I'll do is OK output here to get that value so that the type error that we see is more related. So the trait standard convert from standard format error is not implemented for unit, which is required by result string unit. And the reason we see this error like this is because the question mark tries to use the from trait to convert one error into another for the return value. Oh, why do I have a random n there? What did I do there? Oh no, that's actually the number. Why was I removing that? Okay, so if we want to see what write returns, we can go to the write docs. And we're told because this is a macro, it can do kind of more than a regular function can do. So in this case, the macro returns whatever the write format method returns, commonly a format result or an IO result. And our implementation is coming from format write at the top. So we're looking for format write. So if we pull in standard format error, we can do it like that. But anytime I use the word error, I do like to do a namespaced version of it. So we're going to do FMT error and we'll pull in STD format, standard format. We could also pull in core format, but we're doing a bunch of allocations in this program already. And this is saying empty string literal, so we can get rid of that and that should work just fine. So if we run this and we let debug grid run, so we'll have to run it here. This is now a error that we have to handle. So in this case, what I'm going to do is add a little bit of context to it. And this is just kind of like a shortcut here. We could have a more structured error, but instead I'm just using the miet macro. Debug failed to write to string, or I could say output here. And then I want that error around, so I'm going to format that in. So now we can handle that with the question mark because we're using miet result string here. So to write a file, we'll pull in standard fs file. We'll create a file called output.txt. We're going to use write all here. So we have standard IO write. These question marks would need to be handled. We could handle them again more strictly with variants and such, but I'm going to take a shortcut and I'm going to use the miet macro once again. And this is failed to create file. This is failed to write to file. And now we have error handling, which will tell us if any of these 3 steps fail, all of which can, with messages about why they would fail. I don't expect them to fail, but I figured I would do that. We pulled in write multiple times now, so we have kind of a conflict here. So we can actually solve that by not really pulling this in and using as underscore. And we should be able to look at output and zoom this way out. And look, there's a picture of a tree. So I don't know how in the world we were supposed to figure out that this was what it was supposed to look like. No idea, not a clue. I don't know how we would have found this. It is 7,000 steps into this program. So I would have just been totally guessing. They really need to take a screenshot of this and put it into the problem if they expect people to look for this. I truly have no idea how you were supposed to know which of these steps was the right one to go for or how to figure out which one would have been. But if you are having trouble, this is what it's supposed to look like. It is supposed to be just a bunch of unique values. Let's get rid of this hash map here. We'll get rid of some of this extra code that doesn't need to exist anymore. I'm going to get rid of, or not get rid of, but I'm going to comment out the file writing here now that we have the output. The output for me doesn't live in day 14, so I'm going to stick that in day 14 here. It is an Easter egg, not input, so I feel comfortable committing it. I think it's important to be able to show people what the Easter egg is supposed to look like. And then instead of constructing this hash set, we could also do robots.iter.map robot position position all unique, which comes from iter tools. And this could also have been our test. So if we run this, that also runs and works. So I'm going to leave both versions of that code in here. I'm going to leave the debug stuff in here if you want to look at it. I'm going to leave the imports here that we have set up, et cetera, et cetera. So if you want to look at any of that, do that. The tests don't matter anymore, I guess. So I'll delete those. And that's it. So let's cover part 2, I guess. We have a parser here. We've got a separated list of line endings. I got rid of the input, but the input looks like this. Bunch of robots with a P equals, which is a position, and a V equals, which is a velocity. So separated list, at least one of them has to match. Line endings at the end for separating them. Each of the lines is a separated pair where it starts with a position or a velocity and then parses an IVEC2 separated by space. We broke out this parse IVEC2. I could probably drop this into a utils file and reuse it. We parse, I feel like, IVEC2s often enough. We created our own struct to hold these positions and velocities, makes it really significantly more readable in our code later to remember what is what. And then once we have our list of robots, we literally just loop and move the robots in the position that they're supposed to go. So this is a mutable vec, or rather a variable containing a vec that we can mutate. We iterate using iter mute for the robots, which gives us an exclusive reference, and mute robot, which means that we can set the position equal to the position plus the velocity and use rem Euclid on the map size because these are all IVEC2s. So we get, vector math, which is really nice. We don't have to keep doing like .x this, .y that. So once we've done that to all the robots, then we add one to the step. We test to see if all the robot positions are unique. If it is, we break I, which returns from this loop with a value, which we can then return as our answer. So that's it for today. Part 2, I don't know what they were thinking. Honestly, I don't know how you would have figured this out. It takes 7,000 steps to get there. I don't know. There are so many ways you can code an ASCII Christmas tree. I would have had to look through 7,000 photos to find that. I guess maybe they're expecting you to go all the way back to the other puzzle. I don't know. If you know where in this program it says what a Christmas tree looks like, please let me know in the comments because I very honestly have no idea. I can't find it anywhere. And I don't know how you're supposed to know what to look for. But that's it for today. I hope you didn't get too hung up on part 2. I hope you ran into it and then said, oh, what is that? And looked it up. Or you were able to figure it out pretty quickly. And that's it for today. I'll see you in the next one. Have a great rest of your day.